Let's talk about the difference between an empirical formula and an actual formula. The empirical formula is the smallest whole number ratio of elements in a compound. Ionic compounds like sodium chloride, potassium sulfate are really crystals of alternating cations and anions. So what we call a formula unit is really the empirical formula, the smallest whole number ratio. Covalent molecules, on the other hand, have actual molecules. So the empirical formula and the actual formula could be very different. If we can find the empirical formula through experimentation, and we can find the molar mass through a different experimentation, we can find the chemical. Now, before we decide whether or not something's an empirical formula, we have to look at the chemical formula. So let's start with A. N2O4 is a molecule. That's how it exists in the laboratory. But it's not an empirical formula because we can divide both and call it NO2. NO2 is the empirical formula for N2O4. Whereas C6H5Br can't divide this by anything to make a smaller whole number ratio, so it is an empirical formula. So pause for a second, and for each of the rest, C through H, decide whether or not it's empirical or not, and if it's not, find the empirical formula. Okay, are you ready to see the answers? Let's take a look. Okay, so you can see that C6H5Br, KMNO4, which is ionic, and Fe parentheses OH parentheses 3, which is also ionic, are all empirical formulas, as well as the formula for sucrose. Whereas the formulas for cyclohexane or hexene, we don't know which one, glucose, and nitrogen gas are all molecular formulas. We can divide by the smallest whole number to get empirical formulas. So C6H12 has the empirical formula of CH2. There are lots and lots of compounds with the empirical formula CH2. Everything that is a cycloalkane, and all hydrocarbons with one double bond all have a formula CH2. So figure out which of these has an empirical formula of CH2. There may be more than one. So pause, figure it out, and start again when you're ready. Okay, have you figured it out? One of the things you should have seen is that the molar mass of CH2 is 12.01 plus 2 times 1.01. So that's 14.03 grams. So any number in here that is a multiple of 1403 grams will work. So you can see that I've highlighted both the answers that are plausible molecular masses if the empirical formula is CH2. That will help us figure out what the molecular formula is for a variety of molecules. So here's an example of aspirin. Figured the following mass percent composition: 60% carbon, 4.48% hydrogen, and 35.52% oxygen. So first we're going to figure out the empirical formula, then the molecular formula. If it's given in grams, we use grams. If it's given in percents, though, we pretend we have a 100-gram sample. Therefore, 60 grams, or 60%, is carbon, 4.48 grams is hydrogen, and 35.52 grams is oxygen. And that's our given. We want to find the empirical formula. In order to find the empirical formula, first we're going to convert each of the masses to moles. So I have my 3 masses, and I can use the molar mass of each element. And that's pretty simple division. And that's the first step. And it says that sig figs aren't an issue because we end up with whole numbers, but when we're doing the division, we want to try to keep as many decimal places as possible. If you round too early, you can end up messing up your empirical formula. So step 2 was to convert everything to masses. Step 3 was to divide each of these 3 answers by the smallest. And it turns out that the smallest was 2.2. And I get what we call as a pseudo formula. And I'm going to show this process out, but in fact I rarely write it all out. So my formula would be C 2 1/4 H2O1. But we can't possibly have a chemical formula that has a fraction in it because atoms only come in whole numbers. So take a look at the next page of notes. And we have these fractional subscripts. This is something that you just need to know, and you probably know most of them already. If you end up with a 0.2, that's a fifth. 0.25 is a fourth. 0.33 is a third. 0.4 is 2/5. So if the subscripts aren't whole numbers, multiply them as it's shown in this chart. So we end up with C 2.25 H2O, and because it ends with 2.25, we're going to multiply everything by 4. Multiply it out, and I end up with C9 H8O4. So that's the correct empirical formula. In order to know the actual formula, I also need to know the molar mass. In this case, 300.3 grams. So we should be able to find the molecular formula. The empirical formula, as we calculated it, was C9H8O4 is 180.17 grams. If I find that the molar mass of this compound is 360.3, then we can figure out that the molecular formula has to be C18H16O8. We have to double 180.17 to get 360.3. We have to double C9H8O4 to get C18H16O8. So in a minute, you're going to have a chance to try this. Now we're going to take a look at ibuprofen. Pause the video and see if you and someone near you can figure out the empirical formula. When you're ready, you can start again. Okay, let's take a look at what we did. First thing I did was convert everything to moles. And I ended up with 6.302 moles of carbon, 8.73 moles of hydrogen, and less than a mole of oxygen. Divide all 3 by the smallest, and I end up with 6.5, 9, and 1. 6.5 can't possibly be a correct empirical formula, but if I multiply it by 2, 6.5 times 2 is 13. So if I multiply all of these by 2, the empirical formula for ibuprofen, and it also happens to be the molecular formula, is C13H18O2. That's how you find empirical formulas. And the homework has several problems for you to practice that are just like this. So, good luck. In our next video, we're going to see what happens when we use a combustion reaction to try to find the empirical formula.